everyone. I want to just remind you about the end of the chapter problems in the textbook. On folio, you can see the tab called Textbook. It has the custom LibGuides textbook, which is basically content borrowed from OpenStax. And you have end of the chapter problems. I highly recommend that you do these problems as a practice for your exams. And answers are also provided, so you can check your work. And if you run into any problems, feel free to email me or use my office hours and SI sessions. I also want to remind you that after the deadline for worksheets, the answers are posted. It will be in the same folder where you got the worksheets from, okay? Use these two resources to practice for your exam and get started on your practice as soon as possible. In this lecture, we are going to look at some more stoichiometry, but we're also going to talk about specific types of reactions and then do stoichiometry for those reactions. We already said what combustion reactions are. Basically, combustion means anything burning. It produces a lot of heat. What are these reactions? These are reactions with oxygen in the atmosphere. Oxygen supports combustion, okay? And one thing you need to remember is if you burn hydrocarbons, that means if your hydrocarbons are undergoing combustion, then the products are always water and CO2 gases, okay? Since we discussed already combustion and related stoichiometry in the previous videos, I'm going to focus on precipitation and neutralization reactions in this lecture, and oxidation reduction will be another video. Let's get started. Before we get to precipitation reactions, we're first going to understand how substances dissolve in water. We know that a lot of substances dissolve in water. For example, sodium chloride dissolves in water. You should know that sodium chloride, the substance that you're dissolving, is called solute, and water here is the solvent. Together, they make a solution, and this is an aqueous solution because water is the solvent. So anytime you have water as a solvent, that solution is called an aqueous solution. And this is how we write sodium chloride dissolved in water. Sodium chloride with the state as aqueous. So this is suggesting that it's sodium chloride dissolved in water. It's a solution. What kind of substances dissolve in water? Let's look at a water molecule. It has a classic bent shape. There is the angle between the hydrogens is no longer 180. It's less than 180. And oxygen has these lone pairs, meaning the electron pairs that are not bonded to anything, okay? Oxygen is a very electronegative element. Electronegative means it has the tendency to attract electrons. So you can imagine where the electrons in these bonds are spending more time. They're not shared equally. They're going to spend more time at oxygen because oxygen likes to attract electrons. These are drawn more towards oxygen. So you can see that oxygen is going to be slightly negative than the hydrogens. So we put these delta negative on the oxygen. Delta means partial. So oxygen is going to be slightly negatively charged and hydrogens are going to be slightly positively charged. This type of molecule, which has positive end and negative ends, it's called a polar molecule. So we can say water is a polar substance because the water molecule has positive and negative ends. Think of it like a tiny electrical magnet with positive and negative end. Okay, so now you can think about what kind of substances dissolve in water. You can say polar substances dissolve in water because polar substances also have positive and negative ends. Here's an example of ethanol, and the oxygen end of ethanol is negative. The hydrogen end and the carbon ends are slightly positive. So why would a polar substance dissolve in water? Because when you put a polar substance in water, the Negative charges on the polar substance can interact with the positively charged hydrogens, and the positive ends in the polar substance can interact with the negative ends of water. Okay, so that's why polar substances mix with this water, which is also polar, because the negatives and positives can interact with each other. Similarly, you can also think about why sodium chloride dissolves in water. Sodium chloride is an ionic substance. It has positive ions and negative ions. So when you put sodium chloride in water, the oxygen, so imagine lots of water molecules surrounding this sodium chloride. Now the oxygen ends are going to point towards sodium ion because sodium ion is positive and oxygen in water is negative. And the hydrogen ends, so imagine lots of water molecules coming in with the hydrogen ends pointing towards chlorine. So imagine lots of waters here. With the hydrogen ends are slightly positive. So they are going to interact with the chlorine. And if these interactions are stronger enough, if lots of these interactions, if they are strong enough, they will rip apart this attraction between sodium and chloride ion. Okay, so when you dissolve sodium chloride, the positive and negative ions interact with water. And not only just that, the sodium and chloride ions, their ionic bonding breaks. Okay, so this sodium chloride crystal, it splits into sodium and chloride ions. Okay, so here's the key difference that we are talking about, the difference in how ionic substances dissolve in water and polar substances dissolve in water. Ionic substances break apart into ions. So we can represent that with a equation. So if you have sodium chloride dissolved in water, that means sodium chloride aqueous, you can show that it is breaking apart into sodium ions, which will be dissolved in water, plus chloride ions, and these also will be dissolved in water. Okay. Molecular substances, on the other hand, they dissolve without breaking into ions. Okay, that's a key difference. Both these dissolve, both ionic and polar dissolve because both can interact with water. But there's a key difference in how they dissolve. Ionic substances split apart into ions. Polar substances, they dissolve without splitting apart into ions. So when ethanol dissolves, it's not going to split into carbons, hydrogens, and oxygens. No, we don't get ions like we get here. So you can see that in this animation here. I'm going to use two YouTube videos to demonstrate. So here's sodium chloride dissolving in water. As you can see, water molecules are coming in and dislodging the positive and the negative ions. So the positives move away from the negatively charged ions in this ionic compound, okay? Here you are seeing sugar, which is a molecular substance dissolving in water. So under the magnifying glass, you don't see this with magnifying glass, but let's say you were able to zoom in and see the molecular view. What you're seeing there, those clump of molecules, the brown colored molecules, that's sugar molecules. And you can see how they are dissolving in water. They're separating from each other, but the atoms within them are not separating. The carbons, hydrogens, and oxygens in the sugars, they are not separating from each other. The molecules are separating from each other, but not the atoms themselves. So this is the key difference, how a molecular compound dissolves versus an ionic compound dissolves. Next, we are going to learn how to predict if a compound dissolves in water or not. And here's a solubility chart or solubility guidelines. These tell you which ions are soluble and which ions are insoluble. And there are some exceptions to these rules. Okay, so if you have a compound, for example, let's do some examples. Let's say you have potassium chloride. Is this soluble or not? As you can see here, Any group 1 cation containing compound is soluble in water, and potassium is in group 1. So since this compound contains potassium, we can say this is soluble. So this will be soluble. Okay? It means potassium chloride is going to dissolve in water and make a potassium chloride aqueous solution. What does it contain? This aqueous solution contains potassium ions and chloride ions. Because as we said, ionic compounds dissolve by splitting into their respective cations and anions. Okay. Here's another example. Would silver chloride dissolve in water? Please determine this before I discuss the answer. As you can see, chlorides are usually soluble, but there are some exceptions. So if chloride is combined with silver, it won't dissolve because its silver ion is an exception to the solubility of chloride. Since we have an exception, silver chloride is insoluble. That means the state is going to be silver chloride solid even when you put it in water. If you put silver chloride in water, it's just going to clump at the bottom. Okay, not much of it will dissolve. Okay, so we can practically say this is insoluble. So all of the silver chloride that you put is going to clump at the bottom. We can say the state is still solid. Okay, silver chloride is a solid to begin with. Now, what about um, ammonium phosphate? What about ammonium phosphate? Here's the formula for ammonium phosphate: NH4 thrice PO4. Let's determine if this is soluble or not in water. Phosphates are usually insoluble, but there are some exceptions. So if it is combined with an ammonium ion, it's soluble. And you already learned here that any ammonium ion containing compound is soluble. Okay, so this one is a soluble compound. It's soluble in water. Soluble. Okay, so I can write ammonium phosphate solution, aqueous solution of that. It's going to have three ammonium ions. There will be three ammonium and one phosphate. Phosphate is PO4 3 negative for every one ammonium phosphate. Okay, when you dissolve one ammonium phosphate, you're going to get three ammonium ions and one phosphate. Most students end up breaking this into nitrogen, hydrogen, phosphorus, and oxygen. No. An ionic compound breaks into its ions. So this is one ion, and this is one kind of ion. Okay, ammonium and phosphate. And since there are three ammoniums, you get three ammonium and one phosphate. That's how you have to write the equation for ammonium phosphate dissolving in water. Okay, so you can use the solubility chart to determine most common compounds, the solubility of most common compounds, whether they are soluble or insoluble in water. We are ready to understand precipitation reactions now. Yay! So what are precipitation reactions? These are reactions where when you mix aqueous solutions, aqueous means a solution with a dissolved compound, okay? These are going to be clear because they let light pass through them. The compound is completely soluble, okay? Now, when you mix these two clear aqueous solutions of ionic substances, if you generate an insoluble solid, that's a precipitation reaction. So as you can see here, I have clear solution in this beaker. Clear doesn't mean colorless. It could have color, but what I mean by clear here is light can pass through it, okay? It's clear because it contains a compound that is dissolved in it, okay? And same here, you're pouring an aqueous solution, okay? Now when you mix them together, you're making a solid. So the solution is going to become cloudy and light cannot pass through it. Okay, So if you mix two clear solutions and then you saw a suspension, then you saw that light cannot pass through it. Suddenly there is a solid particles, there are solid particles inside it, okay? You know that it's a precipitation reaction. This solid that is formed, we call it precipitate. We call it precipitate, okay? This is an example of mixing potassium iodide. So you're mixing potassium iodide dissolved in water with, and the solution in the beaker here is lead nitrate, lead 2 nitrate. This is the formula for lead 2 nitrate and dissolved in water. Mixing those two will generate a precipitate which is yellow in color. Let's see why the precipitate is formed. Let's understand. And since you studied the background, since we discussed the background about how substances can dissolve, now I hope you will understand what I'm going to say. So here's my beaker again. So we have, this was your potassium iodide. This is potassium iodide. And as I said, potassium iodide, if it dissolves in water, it's going to contain ions because ionic compound dissolves by splitting into ions. So there we have this solution containing potassium and iodide ions. Now the solution in the beaker, we said the clear solution in the beaker, we said it is lead nitrate. And again, lead nitrate dissolves in water by breaking apart into ions. So this solution, this clear solution to begin with, should have contained lead ions and nitrate ions. Nitrate is a clump of nitrogen with 3 oxygens. So that's a nitrate ion, what you're seeing. Okay, so this solution contains ions, this clear solution contains ions. Now when you mix them together, the ions can bump into each other. Okay, when the positive ions bump into the positive ions, nothing is going to happen. Okay, but something interesting happens when the positives bump into the negatives. Okay, let's say the potassium ion bumped into the nitrate ion. Okay, then you get potassium nitrate. So you have potassium and iodide ions in one solution. You have lead and nitrate ions in the other solution. Now the positive ion can combine with the negative ion in the other compound, okay? So you get potassium nitrate. But potassium nitrate is not soluble, so it's going to split. Potassium nitrate, it's not soluble. So those ions are not going to stick in water because potassium nitrate can dissolve in water. So those two ions are going to move apart again because potassium nitrate dissolves in water. But what if lead and iodide come together? What if lead and the iodide ions come together? Let's bring our solubility chart. You can see here, iodide is insoluble with lead. Okay, this is an exception. If you have iodide with lead, that's an exception to solubility, meaning lead iodide is an insoluble compound. Okay, so now those lead and the lead ions are going to stick to the iodide ions and form this solid lead iodide. Okay, that's your solid now. The lead and the iodide ions stick together to create this ionic solid, which is your precipitate. Okay, so the precipitate here is lead iodide. The formula is PbI2. Okay, lead has 2 plus, iodine has 1 negative. So look at the formula now. When you do crisscross, lead iodide will be PbI2. That's the correct formula for lead iodide. For every 1 lead ion, 2 iodides are going to stick to form this lead iodide compound, precipitate. Now we are going to learn how to write a reaction, okay? So we are going to first write our, what we call the molecular reaction. That means we are going to put the products and the reactant molecules. So let's get started. We have the reactants. We know that the reactants are potassium iodide and lead nitrate. So we put the formulas for those two. Potassium iodide is Ki, and lead 2 nitrate will be PbNO3 twice. This is coming from how we what we learned about how to make a chemical formula. Lead has 2 plus charge. Nitrate is NO3 negative, so the formula should be PbNO3 twice. Now, we're going to, this reaction is basically the ions are getting exchanged, right? The cation from one is going with this anion, so you put it together, you exchange the cations and anions, okay? And the anion here, you put it together with the cation in the other compound. These kind of reactions are called double displacement reactions, okay? So double displacement reactions are reactions in which the cation from one is going with the, is sticking to the anion from the other, okay? You exchange these and write out the products. So your products are going to be potassium nitrate and lead 2 iodide. We're going to write the formulas for those. Potassium is K plus, nitrate is NO3 negative. So potassium nitrate's formula is just, when you do the crisscross, it's just KNO3. Okay? And lead nitrate's formula is PbI2. Potassium nitrate is soluble in water, so you should put AQ beside it, saying that it's an aqueous solution of potassium nitrate as well. And lead iodide is your precipitate, so you should put a solid beside it to show that this is the precipitate that is generated. Okay, so this is your precipitate. Okay, this another way to by the way, we have to balance this reaction. Let's not forget to balance. Okay, we have 2 nitrates, so we needed 2 there. And that will give us 2 potassiums, so we needed 2 here as well. So you would put coefficient of 2 and 2 to balance it. As you can see, every ion is balanced. You have 1 lead on the left, 1 lead on the right, 2 iodines on the left, 2 iodines on the right. This reaction is balanced. Now there is another way to show the same reaction. It's called the net ionic equation. Okay, so another way to write it is basically by showing the true nature of these compounds. Potassium iodide, when it is dissolved in water, the potassium and iodines are no longer together. So this is somewhat of a, it's not telling the truth if we write K and I together like this, right? Because potassium iodide dissolved is basically potassium and iodide ions. This is split apart. So we are going to split the ions and write an equation now. This is called the ionic equation. So potassium iodide, since it dissolves, we're going to split the ions. So 2% potassium iodides dissolved should produce 2 potassiums and 2 iodides. And lead nitrate dissolves in water, so we are going to split that as well. So you should get lead ion and 2 nitrate ions. Okay, that's what we have on the left. And then on the right hand side, potassium nitrate, this is also in dissolved form. You can see potassium and nitrates, they're dissolved in water. You can confirm from the solubility chart if you want. So we are going to split that apart as well. You have potassiums and nitrates, and 2 of each because the coefficient is 2. And lead iodide, it's a solid now in the product. Okay, so the ions are no longer, um, they stick to each other, right? So now potassium and lead, they stick, so we don't split it apart. We're going to write it as it is with the ions stuck together. Okay, now we can cancel out, we can treat this like an algebraic equation, and we can cancel the ions that are common to the left and right. So we have 2 potassiums on the left, which cancel out the 2 potassium ions on the right. We have 2 nitrates on the left, which cancel the 2 nitrates on the right. So what you're left with is 1 lead with 2 iodides, making 1 lead iodide. So this is it. Whatever is left is called your net ionic equation. Okay? Net ionic equation is basically telling you the true species that are reacting. The potassiums and nitrates, we are canceling them out. That means they're not really reacting. Potassium started out as ions, nitrates started out as ions, and after you mix the 2 chemicals, they're still in an ionic state. Okay? Nothing happened to them. But lead ions and iodide ions, which started out as free ions, have combined together to form an insoluble compound. So that is the true reaction that is going on at the molecular level. We call this net ionic equation. How to write it out? The easy way to write it out is figure out which one is your precipitate. Okay, put that on the left, on the right, and the ions, the lead and the iodide ions will be on the left. Okay, all right, and we have a name for the ions that you cancel out. These are called, so the potassium and the nitrate ions, which you basically canceled out in the equation. They're called spectator ions. Spectator ions. They're not doing anything. They're watching the show. They're just how they began. Okay? They're called spectator ions.